There are things in space that don't follow the script we've written for them. Objects that move when they shouldn't. Comets that change direction mid-flight. And sometimes, if you're paying close enough attention, you catch them in the act. Those moments when the universe reveals something unexpected are what drive astronomy forward, challenging our assumptions and forcing us to reconsider what we think we know.
Right now, there's something out there that's rewriting the rules. An object called Comet Atlas, racing through our solar system on a trajectory that suggests it came from somewhere else entirely. Interstellar, a visitor from beyond the gravitational boundaries that define our sun's domain. But that's not the strange part. Interstellar objects, though rare, have been detected before. The strange part is what happened when multiple telescopes turned their attention toward it and watched something no comet should ever do.
Imagine you're observing a spacecraft approaching the sun. It fires its thrusters forward to slow down, bleeding off velocity as it falls deeper into the gravitational well. Then, weeks later, it reverses thrust and accelerates in the opposite direction, pushing itself back outward. That's trajectory correction, intentional course adjustment, the kind of maneuver that requires planning, control systems, fuel reserves, and most importantly, intelligence behind the decisions. Now replace that spacecraft with a comet, a frozen chunk of ice and rock that's supposed to be passive, inert, governed only by gravity and the gentle but inexorable pressure of sunlight. That's what we're dealing with. That's what has astronomers around the world staying up late, comparing notes, double-checking calculations, and quietly asking questions they're not entirely comfortable voicing out loud. Before we go further, let me be clear about something fundamental. What you're about to hear isn't speculation based on a blurry photograph taken by an amateur astronomer, or a single ambiguous data point that could be explained away as instrument error. Multiple observatories, professional facilities with decades of experience, have documented this phenomenon. The Hubble Space Telescope, humanity's premier optical observatory orbiting above Earth's distorting atmosphere. The Nordic Optical Telescope, a ground-based facility with excellent tracking capabilities. Other observatories across different continents, each with their own instruments, their own calibration procedures, their own teams of observers. They've all seen it. Frame by frame, image by image. A transformation unfolding in real time across months of continuous monitoring. The comet was first caught doing something unusual during the summer months. Hubble captured an image showing a bright emission pointing directly toward the sun, not away from it, streaming behind the comet as physics textbooks would predict, and as every well-behaved comet has done throughout recorded history. Toward it. Against the flow of solar radiation that should be pushing everything backward. Astronomers call this an anti-tail, a sun-facing glow that defies the usual radiation pressure exerted by sunlight on small particles. It looked like the comet was venting gas and dust forward, fighting against the very force that should have been dominating its appearance, creating thrust in a direction that makes no sense for a passive object governed solely by sublimation physics. Then, something changed. Over the following weeks, observers watched that forward-facing emission gradually fade. It didn't disappear overnight. It wasn't there one day and gone the next. It dimmed slowly, methodically, while simultaneously a new structure emerged behind the comet, streaming away from the sun exactly as conventional physics predicts. The Nordic Optical Telescope documented this transformation through late summer and early fall, capturing the slow reversal as it played out across August and September. This wasn't a sudden flip, like someone threw a switch or activated a different mode. It was methodical, gradual, patient. A transformation that unfolded over weeks, while the comet continued its hyperbolic plunge toward the inner solar system, falling deeper into the sun's gravitational embrace. And that gradual nature is precisely what makes conventional explanations so difficult to accept. Because if this were just a trick of viewing geometry, an optical illusion created by Earth's changing position relative to the comet's trajectory as both objects move through space, the transition should look different. It should correlate with our orbital motion in predictable ways that geometric models can capture. Astronomers understand projection effects extremely well. They've been dealing with them since Galileo first turned a telescope skyward. But when scientists accounted for perspective shifts, when they corrected for how projection can fool the eye, when they ran the numbers through orbital mechanics software that simulates viewing geometry, the reversal remained. It wasn't an artifact of where we were standing. Something physical changed about where and how this object was emitting material into the vacuum of space. Let's talk about what happens when a comet ejects gas and dust, because understanding the physics is crucial to appreciating why this observation is so troubling. That material carries momentum. It has mass and velocity, and according to Newton's laws that have governed our understanding of motion for over 3 centuries, it pushes. Basic physics tells us this creates thrust, a reactive force pushing the nucleus in the opposite direction. If you're venting material toward the sun, you're generating thrust that slows your orbital motion, acting as a brake on your headlong fall into the inner solar system. If you reverse that jet to point away from the sun, you're now accelerating in the opposite direction, adding velocity that pushes you outward faster than gravity alone would dictate. For an object on a precisely calculated trajectory through the solar system, such a reversal should show up clearly in its motion. The orbit should deviate from what pure gravity predicts, not by huge amounts necessarily, but by measurable quantities that accumulate over time. The object should be somewhere slightly different, perhaps by thousands of kilometers, than where Newton's and Einstein's equations say it should be if only gravity were acting on it. These deviations, called non-gravitational accelerations, are routinely measured for comets. They're a standard part of orbital analysis, quantified and cataloged by professionals who track near-Earth objects. But here's the puzzle that's keeping researchers up at night. The observation that doesn't fit neatly into any simple explanation. Comet Atlas isn't showing significant non-gravitational acceleration. Its path matches what gravity alone predicts, within the margins of measurement error that represent the limits of our observational precision. That means one of 3 things is happening, and none of them are entirely satisfying. Either the jets are perfectly balanced, pushing equally in all directions so the forces cancel out in a conspiracy of symmetry that seems statistically unlikely. Or the object is so massive that the recoil from its outgassing is negligible compared to its inertia, barely nudging something with the mass of a mountain. Or something else entirely is going on that hasn't been fully considered. Some mechanism or process that lies outside the standard models we use to understand cometary behavior. Between summer and late fall, tracking across multiple months of observations, this comet shed approximately 2 million metric tons of material into space. Take a moment to visualize that figure. 2 million metric tons. That's roughly the equivalent of 3 Empire State Buildings, those massive Art Deco skyscrapers that dominate the Manhattan skyline, completely evaporating into the void over just a few months. Every gram of that material carried momentum as it left the nucleus. This mass loss creates thrust through the rocket equation, the same fundamental physics that powers spacecraft from chemical rockets to ion engines. Every action produces an equal and opposite reaction, a principle so fundamental that it appears in introductory physics textbooks worldwide. For typical comets, this rocket effect is measurable and shows up clearly as deviations from purely gravitational orbits. Small but detectable accelerations that accumulate over time. Astronomers catalog these as non-gravitational forces in their orbital solutions, fitting mathematical models to observed positions and extracting parameters that quantify how much thrust the comet is experiencing. But Comet Atlas shows minimal such acceleration. Its trajectory matches what gravity alone predicts, with orbital residuals, those small differences between predicted and observed positions, remaining within observational uncertainty. The signal, if it exists, is buried beneath the noise of measurement error. This absence of detectable recoil places powerful constraints on what's happening physically. If you know the rate at which mass is being ejected, measured from the brightness and extent of the coma, and you know the velocity of that material as it leaves the nucleus, estimated from spectroscopic line widths and thermal models, you can calculate the thrust force using the fundamental rocket equation. For that thrust to barely affect the object's motion, to produce acceleration smaller than we can measure, the nucleus must be massive enough that the force barely budges it. It's like trying to push a mountain with a fire hose. The calculation suggests a minimum mass of approximately 33 billion metric tons, with uncertainty ranges that span factors of a few depending on assumptions about dust properties and outgassing geometry. That's substantial. That's not some tiny fragment, a chip off a larger body, tumbling through space. If you assume a density similar to typical comet nuclei, around 600 kilograms per cubic meter, that porous mixture of ice, dust, and rock resembling dirty snow more than solid stone, you end up with a body several kilometers across, multiple kilometers, comparable in size to some of the larger comets we've studied up close with spacecraft that flew past them and sent back detailed images of their surfaces. Comet Hale-Bopp, that spectacular visitor from the mid-1990s, visible to the naked eye for months, had a nucleus estimated at roughly 60 billion tons. Comet Halley, the most famous periodic comet returning every 76 years, mass is about 220 billion tons. This object sits on the lower end of that range, but still qualifies as a genuine celestial body, one massive enough to have survived its interstellar journey intact despite bombardment by cosmic rays and erosion from interstellar gas, and one complex enough to exhibit behavior we're still trying to understand. The most conservative explanation, the one that requires no new physics and no exotic assumptions, the one that most working astronomers would default to when pressed for an opinion, involves compositional changes as the comet heats up approaching the sun. This model builds on decades of comet science, observations of hundreds of comets, and laboratory experiments studying how different ices behave under various conditions. Different ices sublimate at different temperatures, transitioning directly from solid to gas without passing through a liquid phase. Carbon dioxide, for instance, vaporizes at temperatures far below the freezing point of water, sublimating readily even in the cold outer solar system. Even at the chilly distances beyond 3 or 4 times Earth's distance from the sun, where sunlight is dim and temperatures hover around 150 Kelvin, carbon dioxide molecules can break free from their crystalline lattice and stream into space, driven by vapor pressure gradients. As the comet moves inward closer to the sun's warmth, carbon dioxide sublimation intensifies. The rate increases exponentially with temperature, following the Clausius-Clapeyron relation that governs phase transitions. But eventually, if the comet has a layered structure, with composition varying with depth, the surface layers rich in carbon dioxide get depleted. The volatiles evaporate away, leaving behind a lag deposit of dust and less volatile material. Deeper material becomes exposed as the surface recedes, and that deeper material has a different composition. Water ice dominates, mixed with refractory dust, those rocky and carbonaceous particles that don't sublimate at all, but rather get left behind or mechanically released as the ice matrix around them vaporizes and loses structural integrity. Water ice requires higher temperatures to sublimate efficiently. Its vapor pressure remains low until temperatures climb above about 190 Kelvin, which happens closer to the sun, typically inside about 2 astronomical units in the inner solar system, where solar heating becomes intense. The dust released by water sublimation has different properties than dust entrained by carbon dioxide gas. The grain size distribution might differ if water ice trapped different sized particles during formation. The release velocity might be lower because water vapor expands less energetically than carbon dioxide, for thermodynamic reasons related to molecular weight and specific heat. The way particles scatter sunlight changes based on composition and size. with different materials and different diameters producing different scattering phase functions that describe how bright things appear at different viewing angles.
Here's where the compositional transition model becomes elegant, explaining multiple observations with a single underlying physical process. This transition from carbon dioxide-dominated to water-dominated sublimation could flip the apparent direction of emission that we observe from Earth. In the carbon dioxide phase, when the comet is still relatively far from the Sun, smaller ice-coated grains with short lifetimes scatter efficiently at optical wavelengths where our telescopes are most sensitive. These particles, released early in the comet's approach, might create a forward scattered glow visible from Earth's viewing geometry, appearing as that sun-facing anti-tail observers documented with Hubble. Forward scattering happens when light scatters in the forward direction relative to incident sunlight, and small ice particles are particularly efficient at this under certain size and composition conditions. As the regime shifts to water and refractory dust closer to the Sun, larger particles with different scattering properties dominate the visible emission. These create a more traditional tail, pushed away from the Sun by radiation pressure in the classical manner that's been understood since the 19th century, when physicists first realized that light carries momentum. The timing aligns with observations remarkably well. Comet Atlas was around 3 to 4 times Earth's distance from the Sun when the anti-tail was most prominent. Precisely the distance range where carbon dioxide sublimation should be active according to thermal models. But water ice remains mostly dormant beneath its sublimation temperature threshold. This compositional model has precedent in decades of comet observations. Astronomers have documented comets showing seasonal variations in activity, with different regions turning on and off as they rotate and as their distance from the Sun changes through their orbits. Different locations on the nucleus, with different compositions or different thermal properties affecting how quickly they heat up, activate at different times. The lesson from decades of comet studies, from ground-based observations and from spacecraft that flew past comets and studied them up close, is that these objects are heterogeneous, layered like onions, capable of surprising behavior as thermal waves penetrate their interiors and reach volatile-rich layers that suddenly activate. But the transition observed in Comet Atlas seems more abrupt than typical solar system comets, happening over weeks rather than the months or years of gradual evolution usually seen. That rapidity suggests either a sharp compositional boundary inside the nucleus, perhaps created by the comet's formation history in its distant home system, or an unusual geometry of active regions where particular spots on the surface dominate emission. Perhaps the initial sun-facing activity came from a specific location on the surface, a localized jet from an active region, that became inactive as it heated past some threshold temperature, where the near-surface volatiles were exhausted. Simultaneously, a different region on the opposite side, perhaps initially shadowed or insulated, activated as thermal waves conducted through the interior and reached depths containing fresh volatiles. Now we shift into territory that makes most professional astronomers uncomfortable, though we approach it with scientific rigor rather than sensationalism. What if the jet reversal isn't natural at all? What if this comet is executing a controlled maneuver, deliberately adjusting its trajectory, using propulsion that only superficially resembles the random outgassing of sublimating ice? This hypothesis, as carefully worded as it is provocative, rests on timing and directionality. If the sun-facing emission observed earlier acted as braking thrust, pushing the object slightly toward the Sun and therefore reducing its orbital velocity, slowing its fall into the inner system, then the subsequent tail pointing away could represent forward thrust, accelerating the object outward as it swings around its closest approach to the Sun. Such a maneuver would resemble trajectory correction, the kind of propulsive burn a spacecraft makes to fine-tune its path through the solar system, adjusting for navigation errors or setting up for the next phase of the mission. Before dismissing this completely as the sort of wild speculation that belongs in science fiction rather than peer-reviewed journals, consider what observational signatures would actually support such an extraordinary claim. First,
Sustained non-gravitational acceleration beyond what sublimation models predict based on observed mass loss rates and reasonable assumptions about gas velocities and dust properties. If the thrust continues longer than thermal models say outgassing should last given the object's distance from the Sun and estimated size, or if the acceleration is larger in magnitude than the mass loss rate can explain through conventional rocket physics, that's a genuine anomaly requiring explanation.
Second, repeatable reorientation of the jet axis in ways that don't correlate with expected physical drivers. Natural comets can have multiple jets emanating from different active regions, but they're tied to the body's rotation state and the illumination pattern as sunlight hits different parts of the surface. If this comet shows jet direction changes that don't correlate with rotational period or with solar heating patterns predicted by thermal models, that's genuinely strange and demands careful investigation. Third, spectral anomalies in the composition of emitted material. If spectroscopy reveals emission lines from unusual metals, exotic molecular species not typically seen in comets, or abundance patterns inconsistent with primitive solar system or interstellar material, that demands explanation. Fourth, radio or infrared emissions at frequencies or with modulation patterns that can't be explained by thermal radiation or known molecular transitions. An artificial object might emit electromagnetic signatures from internal systems, power generation, communication attempts, or simply waste heat from active components. Fifth, trajectory fine-tuning where the orbit shows characteristics that seem designed rather than random, targeting the inner solar system in ways that maximize scientific return if this were a probe sent to study our star and planets. So far, and this is crucial to emphasize, none of these smoking gun signatures have been definitively detected in ways that would compel acceptance of the artificial hypothesis. But observations are incomplete. The object is faint, near the threshold of detectability even for large professional telescopes. It's moving fast, changing position relative to background stars by amounts that challenge tracking systems designed for slower-moving objects. And it's difficult to observe continuously, given the realities of telescope scheduling, weather, and geometric constraints that limit when and how the comet can be seen from Earth. Gaps in the data mean brief episodes of unusual behavior might have occurred when no telescope was watching, falling into observational blind spots. The absence of evidence is not evidence of absence. That phrase, repeated often in science but sometimes misapplied, genuinely applies here more than in most astronomical puzzles. We haven't looked hard enough, or long enough, or with sufficient sensitivity to rule out all exotic possibilities. The question is whether the observations we do have justify mobilizing the considerable resources needed for intensive follow-up, or whether the prior probability of artificiality is so low that natural explanations should be exhaustively tested first. The stakes extend far beyond one unusual comet, and this is why the debate generates such intensity among researchers who care deeply about getting the right answer. If this object is natural, but exhibiting behavior never documented before in decades of comet observations, it expands our understanding of what interstellar visitors can do, how they're composed, what volatile species they contain, how their internal structure reflects formation conditions in planetary systems around other stars. What happens when bodies from other stellar environments, places where chemistry and temperature and irradiation histories differed from our sun's neighborhood, venture through our cosmic backyard for the first time? If it's something else, if those engineered signatures somehow hold up under the ruthless scrutiny of peer review and independent verification, if every natural explanation is tested and found wanting, then we're facing a discovery that would rank among the most consequential in human history. First contact, or at least first detection of extraterrestrial technology, would immediately become the most important fact about our species' place in the universe. It would answer the fundamental question that has driven SETI searches for decades. Are we alone? The answer would be no, definitively, and everything downstream from that realization would need to be reconsidered. Watching this comet isn't like pointing a telescope at a distant galaxy that sits still in the sky. Its light taking millions of years to reach us, unchanging on human timescales.
This object is moving fast, racing through the inner solar system at velocities measured in tens of kilometers per second relative to the Sun. It changes position relative to background stars by noticeable amounts every single night, amounts large enough to see by eye when comparing images taken hours apart. It's also faint, barely visible even to large professional telescopes, requiring sensitive detectors and long exposure times to gather enough photons for meaningful analysis. Each image requires minutes to hours of integration time, during which the telescope must track the moving target precisely, compensating for its motion to keep it centered on the detector. The observational challenges are considerable and represent the unglamorous reality of professional astronomy. The object's position relative to the Sun as viewed from Earth creates narrow windows when observations are even possible. You need the comet visible above the horizon, not below the horizon where Earth's bulk blocks the view, while simultaneously, the Sun is sufficiently below the horizon to avoid daytime sky brightness that would overwhelm the faint comet signal. That sweet spot, twilight conditions where the comet is high enough and the sky is dark enough, lasts only a few hours per night. And those hours shift as Earth rotates and orbits, sometimes placing the observing window at inconvenient local times or eliminating it entirely when geometry doesn't cooperate. Space telescopes like Hubble have advantages because they're not limited by Earth's daylight cycle, observing continuously as they orbit above the atmosphere. But even they must contend with bright backgrounds when pointing near the Sun, and must follow safety protocols that prevent aiming too close to our star, which could damage sensitive instruments designed for faint object detection. The Hubble Space Telescope operates under strict solar avoidance angles, zones around the Sun and the sky where the telescope simply cannot point without risking catastrophic damage to its optical sensors. Scheduling observations of the comet requires careful planning by specialist schedulers, who must balance competing demands from hundreds of approved programs, catch the object when it's far enough from the Sun and the sky to be safe, and coordinate with the telescope's orbital constraints that limit what parts of sky are accessible at any given moment. Then there's spectroscopy, arguably the most powerful tool in astronomy's arsenal. The process of splitting light into its component wavelengths to reveal what the object is made of, how fast it's moving, what temperature it has, and a host of other physical properties encoded in the spectrum. Taking a spectrum requires concentrating the object's faint light through a narrow slit and dispersing it across a detector using a prism or diffraction grating. That process takes time, often much longer than direct imaging, and reduces signal compared to imaging because you're spreading the light across many pixels instead of concentrating it. For a faint, fast-moving target like this comet, you need a large telescope to collect enough light, good tracking capabilities to keep the target centered in the slit despite its motion, and long integration times, measured in tens of minutes to hours, to build up sufficient signal above detector noise. Few facilities can provide this combination of capabilities on demand. The queue for major instruments fills months in advance with approved programs that underwent competitive peer review. Getting directors' discretionary time, slots reserved for urgent targets of opportunity that couldn't be planned months ahead, requires convincing proposals submitted on short notice and often a bit of luck that a suitable time slot is available. Multiple observatories have contributed pieces to building the dataset on this comet, each providing different capabilities and different perspectives that together create a more complete picture than any single facility could achieve. The Hubble Space Telescope provided that crucial, high-resolution image in optical wavelengths, showing the Sun-facing anti-tail, capturing detail impossible from ground-based observatories fighting against atmospheric blurring. The Nordic Optical Telescope, a capable facility in the Canary Islands, optimized for tracking solar system objects, conducted the sustained monitoring campaign through summer and fall, imaging the comet repeatedly at regular intervals to document the tail evolution week by week. Other large facilities around the world likely contributed spectroscopy, capturing emission lines from gas molecules, photometry at multiple wavelengths measuring colors that constrain dust properties, and high-precision astrometric measurements tracking the object's position with accuracies measured in fractions of an arcsecond. Each telescope brings specific capabilities and specific limitations, reflecting its design priorities and observing conditions. Hubble's pointing stability is excellent, limited mainly by thermal flexing as it moves between sunlight and shadow on each 90-minute orbit. But tracking fast-moving solar system objects requires the telescope to slew continuously during exposure to follow the target, compensating for its motion against the fixed stars. Imperfect tracking creates trailing or smearing, elongating the image in the direction of motion and reducing effective resolution. Ground-based telescopes face atmospheric seeing, the blurring caused by turbulent air cells with slightly different temperatures and densities that refract light randomly, creating the familiar twinkling of stars. Adaptive optics systems compensate partially, using deformable mirrors that change shape hundreds of times per second to correct wavefront distortions measured in real time. But correction is imperfect, especially for faint targets where the wavefront sensor struggles. Weather causes gaps in coverage that are simply unavoidable at ground-based sites. Clouds, obviously, block observations entirely. High winds force telescope closures to protect delicate optics. Poor atmospheric transparency from dust, smoke, or high humidity degrades signal quality even when the sky appears clear. A critical brightening or morphological change happening during bad weather goes unrecorded, creating frustrating holes in what should be continuous monitoring. These are the realities professional astronomers deal with constantly, planning observing campaigns around probability statistics for weather and accepting that some data will inevitably be lost to conditions beyond anyone's control. The power of multiple independent observations cannot be overstated in science, where reproducibility is the gold standard for establishing truth. If Hubble and the Nordic Optical Telescope both see the sun-facing feature at comparable times, that feature is almost certainly real, not an artifact of one instrument's optics or detector quirks or data processing pipeline. If spectroscopy from different facilities using different spectrographs and different calibration procedures both detect specific molecular emission lines at the same wavelengths, that identification gains substantial confidence. Consistency across platforms argues powerfully against instrumental explanations for observed features, and points toward genuine astrophysical phenomena, requiring physical interpretation. But full consistency is rare in the messy reality of observational science. Observers report discrepancies all the time, differences in measured brightness between simultaneous or near-simultaneous observations with different telescopes, slight morphological variations in how the coma and tail appear. Some of that represents real-time variability in the comet itself, which can change on timescales of hours to days as it rotates and as sublimation rates fluctuate with solar heating. Some discrepancy is instrumental, reflecting different detector sensitivities, different point spread functions that describe how point sources blur, different wavelength coverage that samples different parts of the spectrum. Disentangling these effects requires careful modeling, simulating observations with each instrument's actual characteristics, and accounting for differences in resolution, sensitivity, tracking errors, and atmospheric seeing conditions at ground-based sites. Not every strange thing in the sky is actually strange once you properly account for observational biases and projection effects. Sometimes what looks extraordinary is just ordinary physics, viewed from an unusual angle through the limitations of our instruments. This is the first lesson of observational astronomy, learned and relearned across 4 centuries since telescopes revealed that the universe is far stranger than naked-eye observations suggested, but also that our perception is shaped by the tools we use and the vantage point we occupy. A comet ejects material in 3-dimensional space, creating a complex structure with jets, shells, and halos distributed around the nucleus. But we observe it as a 2-dimensional projection on the plane of the sky, collapsing depth information into a flat image. Our line of sight collapses everything along that direction into a single view, As Earth orbits the Sun at 30 kilometers per second, and the comet follows its own trajectory at velocities that can exceed 100 kilometers per second relative to the Sun, the viewing geometry constantly changes. The angle between the Sun, the comet, and Earth evolves continuously, changing how we see the same three-dimensional structure. What appeared to be directed one way can seem to flip as our perspective shifts, an effect familiar to anyone who has watched a fast-moving airplane appear to change course even though it's flying straight. Disentangling real changes in the comet from apparent changes due to geometry requires mathematical modeling of the three-dimensional dust distribution and how it projects onto our two-dimensional view from different angles. The classic case is the anti-tail phenomenon, understood for over a century since astronomers first documented it in detail, but still sometimes misinterpreted when seen in new comets. When Earth crosses the orbital plane of a comet, dust particles that lag behind the nucleus along its orbit, trailing it like breadcrumbs marking where it's been, appear to point sunward when viewed edge-on. This happens because we're viewing the dust trail from a special geometry, looking along the plane rather than from above or below. The particles aren't moving toward the Sun, they're trailing the comet along its path, spread along the orbit by radiation pressure and differential orbital velocities that cause slower particles to fall behind. But from our temporary viewing angle during plane crossing, they project as a forward spike that mimics a sun-facing jet, even though no such jet exists. Astronomers have sophisticated methods for distinguishing real changes from apparent ones caused by viewing geometry. Vector tomography uses observations from multiple dates, spanning a range of viewing angles, to reconstruct the three-dimensional distribution of material that best explains all the observed projections. If you watch the comet from enough different perspectives as Earth and the comet move through their orbits, you can solve for the actual spatial structure. It's similar to how medical CT scans reconstruct three-dimensional images from multiple two-dimensional X-rays taken from different angles, using mathematical inverse problems to work backward from projections to structure. Polarimetry provides another diagnostic tool that helps separate geometry from physics. Dust particles scatter sunlight, and that scattering produces polarization, where the electric field oscillates preferentially in one direction rather than randomly. The degree and orientation of polarization depend on the scattering angle, the angle formed by the path from the Sun to the particle to the observer. Different viewing geometries produce different polarization signatures, even if the dust distribution remains completely static in three-dimensional space. Measure polarization over time as viewing geometry changes, and you can test whether observed morphology changes are consistent with static dust illuminated from varying angles, or whether they require actual redistribution of material in space. The scientists tracking this comet would have been acutely aware of these projection pitfalls, having dealt with similar issues in countless previous observations. Their analysis presumably included geometric modeling, testing whether the observed changes could be explained by Earth's changing position alone, with no evolution in the comet's actual emission pattern. The fact that they reported an intrinsic jet reversal, publishing it as a genuine physical change rather than geometry, suggests their models ruled out pure projection effects within reasonable confidence limits. But ruling out requires assumptions about dust distribution, ejection velocities, grain lifetimes, and other parameters that aren't independently measured with high precision. Uncertainty in those assumptions leaves some room for alternative geometric explanations that might explain part, though probably not all, of the observed reversal. The abruptness of the transition matters crucially in this context. Projection effects tend to be smooth and gradual, as viewing geometry continuously evolves with the stately dance of orbital mechanics. A sudden flip happening over days rather than weeks suggests something intrinsic changed, rather than just our viewing angle gradually sweeping across a static structure. But defining sudden versus gradual can be subjective when observation cadence is irregular, with images separated by days or weeks. If you image once a week, a change that happened over 3 days appears sudden in your dataset, while the same change sampled daily might look smoother and more continuous. There's also the compositional angle that geometry simply cannot explain. Projection effects can't change spectral signatures, the wavelengths and intensities of emission lines from gas molecules. If the emitted material's chemistry shifted over the observation period, with relative abundances of different molecules changing, that's intrinsic to the comet's outgassing, not a consequence of viewing angle. Reports indicate that spectroscopic follow-up detected compositional changes supporting the physical transition model from carbon dioxide-dominated to water-dominated sublimation, though details remain somewhat sparse given the considerable observational challenges of obtaining good spectra of faint, fast-moving objects. Dust grains are not all created equal, and their inequality determines much of what we see when we look at comets through telescopes. Small particles, measuring submicron to a few microns in diameter, have high ratios of radiation pressure to gravitational attraction, meaning sunlight pushes them more strongly than the sun's gravity pulls them inward. The radiation pressure force scales with the particle's cross-sectional area, which goes as the square of the radius, while gravitational force scales with mass, which goes as the cube of the radius. For very small grains below a certain size threshold, radiation pressure overwhelms solar gravity completely. These particles, once released from the comet's nucleus where they were held by the ice matrix, accelerate away from the sun faster than they would fall inward under gravity alone. They form the classical comet tail, that glowing streamer extending millions of kilometers into space, always pointing approximately away from the sun, regardless of the comet's direction of motion. Larger grains, measuring tens of microns across, follow more curved paths, representing a compromise between their orbital motion inherited from the nucleus and the outward push of sunlight. The radiation force is weaker relative to their mass, so they don't accelerate as dramatically. Their trajectories curve gracefully, falling sunward under gravity while simultaneously being blown outward by radiation. The resulting paths create structures astronomers call synchrons and syndynes when modeling dust dynamics. Curves in space connecting particles released at the same time, or particles with the same size, respectively. Grains hundreds of microns across barely feel radiation pressure at all compared to gravity. They're released from the comet with some initial velocity imparted by sublimating gas, tens to hundreds of meters per second, but then follow nearly ballistic trajectories dominated by their orbital motion around the sun. They're essentially tiny asteroids briefly, moving on elliptical or hyperbolic paths determined by their velocity at release and the sun's gravity. Under certain geometric conditions, when viewing angles align just right, these large grains spread along the comet's orbit can appear to point sunward even though they're not moving toward the sun. If Earth's viewing angle aligns with the orbital plane, trailing dust distributed along the comet's past trajectory projects as a forward-pointing feature, even though the particles are actually behind the comet in its motion. This is the mechanism behind classical antitails, geometric features understood since the 19th century, and it's entirely a projection effect, requiring no exotic physics. For Comet Atlas, the question debated among specialists is whether the observed sun-facing glow could be explained entirely by this dust geometry, or whether something more fundamental changed in the outgassing pattern. The answer depends on several factors that aren't measured with high precision: the comet's orbital plane and how it relates to our viewing geometry from Earth, the grain size distribution, the relative numbers of small versus large particles, the grain lifetime, how long particles survive before fragmenting or sublimating under intense solar heating that can drive ice grains to temperatures where remaining volatiles evaporate. The compositional transition model, invoking carbon dioxide versus water ice, suggests small ice-coated grains rather than large refractory ones to explain the initial sun-facing emission. The argument flows from sublimation physics. Carbon dioxide sublimation early in the approach, when the comet is still relatively far from the sun at distances beyond 3 astronomical units, released ice grains that forward scattered sunlight efficiently when viewed from Earth's particular geometry during summer observations. These grains, being small and volatile rich, had short lifetimes measured in days to weeks before solar heating sublimated remaining ice and destroyed the particles. This created a compact, bright feature concentrated near the nucleus rather than extending far into space. As the comet transitioned to water-dominated outgassing closer to the Sun, the grain population changed fundamentally. Larger, darker, refractory particles replaced bright ice grains. Water-ice sublimation entrains dust differently than carbon dioxide because the vapor pressures and gas densities differ, affecting how efficiently dust gets dragged along. The forward scattering from small, bright grains diminished as that population disappeared, while classical backscattering off larger grain tails grew, creating the observed reversal from sun-facing emission to anti-solar tail. The timing supports this interpretation. The transition occurred as the comet moved from approximately 3 astronomical units, where carbon dioxide dominates, to inside 2 astronomical units, where water ice activates. We don't know this comet's grain size distribution with anything approaching certainty, and that uncertainty propagates through every model trying to interpret observations. Direct measurements would require spacecraft instruments flying close enough to sample dust particles and measure their sizes, shapes, and compositions. From Earth, even with large telescopes, we're limited to indirect inferences. Observations provide some constraints through brightness measurements at multiple wavelengths and color indices describing how brightness changes from blue to red light. Different grain sizes scatter different colors with different efficiencies based on how particle size compares to the wavelength of light. But interpretation requires assumptions about composition, porosity, whether particles are compact or fluffy aggregates, whether they're homogeneous or layered. Spectral slope, the mathematical description of how brightness changes with wavelength across the visible and near-infrared, offers clues that modelers use to constrain possibilities. Red colors suggest larger particles or darker materials. Blue colors suggest smaller particles or brighter ices. But the mapping from color to size is degenerate, meaning multiple combinations of size and composition produce similar colors. Breaking that degeneracy requires additional information, like polarization or thermal emission, that samples different aspects of particle properties. Different viewing angles see different amounts of dust even if the total production rate remains constant in time, an effect called aspect angle variation. If the nucleus has active regions concentrated in certain locations rather than uniformly covering the surface, rotation carries those regions in and out of our view as the comet spins. When an active jet points toward Earth, we see maximum dust brightness. When it rotates away, brightness drops. This modulation can mimic changes in activity even when the actual outgassing rate is steady. Disentangling rotation effects from true activity changes requires knowing the rotation period and tracking brightness variations phase-locked to rotation. The dust size sorting explanation permits some anti-tail phenomena naturally within conventional comet physics. Large particles spread along the orbit, viewed edge-on during specific geometric windows, create forward-pointing features without requiring exotic emission patterns. But the scale and timing and spectroscopic evolution of this comet's reversal push the boundaries of what geometric effects and grain size distributions can plausibly explain by themselves. The abruptness, the brightness contrasts between early and late observations, the spectral changes indicating compositional evolution, all suggest more than passive dust trailing or projection tricks. Something changed fundamentally about how and what the comet was emitting into space. Telescopes can mislead if you're not careful about systematic errors and instrumental artifacts, a lesson learned painfully across astronomy's history through false discoveries that turned out to be instrumental effects. Every instrument carries biases, quirks in its optics or detectors or data processing pipelines that can mimic real celestial phenomena if you don't understand them thoroughly. This is why professional astronomers obsess over cross-checks. comparing observations from different telescopes operating under different conditions with different instrumental characteristics. If multiple independent systems using different technologies all see the same phenomenon, confidence grows substantially. The catalog of observatories contributing data to this comet's story spans both ground and space, distributed geographically to provide different viewing conditions.
Hubble captured that crucial image, showing the sun-facing antitail, utilizing its position above Earth's atmosphere to achieve diffraction-limited resolution unattainable from the ground. The Nordic optical telescope provided the monitoring sequence documenting tail evolution, leveraging its dedicated time for solar system objects and automated scheduling that can respond quickly to targets of opportunity. Other facilities around the world likely contributed spectroscopy, capturing emission lines from molecules like CN, C2, C3, and other common cometary species that fluoresce under sunlight. Photometry, measuring brightness in standard filter systems that allow comparison across different telescopes. And high-precision astrometry, tracking the object's position against background stars with accuracies approaching tens of milliarcseconds. Each instrument brings specific challenges, reflecting its design and operating environment. Hubble's pointing stability is excellent, limited mainly by thermal flexing as the telescope's structure expands and contracts moving between sunlight and Earth's shadow on each 90-minute orbit around the planet. But tracking fast-moving solar system objects requires the telescope to slew continuously during exposure, rotating the entire spacecraft to keep the target centered on the detector while compensating for the object's motion against the background stars. Imperfect tracking, arising from limits in how accurately the guide stars can be measured and how quickly the spacecraft can respond to pointing corrections, creates trailing that elongates the image in the motion direction and reduces effective resolution. Ground-based telescopes face atmospheric seeing, the fundamental limitation imposed by Earth's turbulent atmosphere that causes stars to twinkle and extended objects to blur. Temperature variations in air cells create refractive index differences that bend light randomly, distorting wavefronts and mixing photons from different directions. Adaptive optics systems attempt to compensate in real time, using deformable mirrors with dozens or hundreds of actuators that flex the mirror surface to correct measured wavefront errors. A wavefront sensor, typically observing a bright guide star, measures distortions and feeds corrections to the mirror hundreds to thousands of times per second. But correction is imperfect, especially for faint targets where the wavefront sensor struggles to measure distortions accurately, and especially at visible wavelengths where atmospheric effects are stronger than in the near-infrared where many adaptive optics systems work best. Weather causes unavoidable gaps in ground-based coverage that frustrate careful observing campaigns. Clouds block observations entirely, obviously. High winds exceeding safety limits force telescope closures to protect delicate optics and mechanics from damage. Poor atmospheric transparency from aerosols, dust, smoke from distant fires, or high humidity degrades signal quality even when the sky appears subjectively clear to human eyes. Extinction, the absorption and scattering of light by the atmosphere, can vary by factors of 2 or more between excellent and marginal conditions. A critical brightening event or morphological change happening during bad weather goes entirely unrecorded, creating frustrating holes in what should ideally be continuous monitoring. These realities are simply part of doing astronomy from Earth's surface, and observers plan campaigns accounting for statistical probabilities of usable weather based on decades of site monitoring. The power of multiple independent observations providing mutual validation cannot be overstated in science, where reproducibility is the gold standard separating robust findings from artifacts or errors. If Hubble and the Nordic telescope both see the sun-facing feature at comparable epochs within days of each other, that feature is almost certainly real, rather than an artifact of one instrument's particular optical configuration or detector quirks or image processing choices. If spectroscopy from different facilities using different spectrograph designs, different wavelength coverage, and different calibration procedures all detect specific molecular emission lines at the same wavelengths matching laboratory measurements,
that identification gains substantial confidence, approaching certainty. Consistency across platforms argues powerfully against instrumental explanations for observed features and points compellingly toward genuine astrophysical phenomena requiring physical interpretation rather than technical debugging.
But achieving full consistency is rare in the messy reality of observational science, where multiple factors introduce scatter and variation. Observers routinely report discrepancies, differences in measured brightness of 10 to 20% between simultaneous or near-simultaneous observations with different telescopes. Slight morphological variations in how the coma and tail structures appear in images processed differently. Some of that scatter represents real-time variability in the comet itself, which genuinely changes on timescales of hours to days as it rotates carrying different active regions into sunlight, and as sublimation rates fluctuate, responding to changing solar illumination or internal pressure variations. Some discrepancy is instrumental, reflecting different photometric systems, different detector sensitivities varying with wavelength, different point spread functions describing how point sources blur, different ways of subtracting background skylight that affect measured fluxes. Disentangling physical variability from instrumental scatter requires careful modeling that many researchers don't have time or resources to pursue thoroughly. You simulate observations with each instrument's actual measured characteristics, accounting explicitly for differences in wavelength response curves, spatial resolution, field of view, and noise properties. You process simulated data through the same pipelines used for real observations and check whether predicted discrepancies match observed ones. When they do, instrumental effects are understood. When systematic offsets remain after accounting for known instrumental differences, physical explanations become necessary. Science is done by humans, and humans bring all their complexity to the endeavor, whether we acknowledge it or not. Egos, ambitions, career pressures, institutional politics, the very human desire to be first, to be right, to make the discovery that gets remembered. We like to think scientific truth emerges cleanly from data, analyzed objectively, using rigorous mathematical methods. But the path is invariably messier when you look closely. This is especially evident when a high-profile scientist with media connections stakes reputation on a controversial idea that challenges conventional thinking. Abraham Loeb is not just another astronomer publishing papers read mainly by specialists in obscure journals. He's a former chair of Harvard University's Astronomy Department, one of the most prestigious positions in the field globally. He's a prolific author with hundreds of peer-reviewed publications spanning cosmology, astrophysics, and astrobiology. He's a public intellectual who engages media with enthusiasm most academics carefully avoid, appearing on podcasts, writing op-eds, giving interviews where he articulates ideas in ways non-specialists can understand. He's known among colleagues for bold hypotheses, a willingness to entertain ideas that peers dismiss as too speculative or poorly constrained by available data. Oumuamua, that first confirmed interstellar visitor that passed through the solar system years ago, became a vehicle for Loeb's advocacy around technosignatures, observable signs of extraterrestrial technology that SETI programs search for. He proposed publicly, in papers and interviews, that it might be a light sail, an artificial structure pushed by radiation pressure rather than a natural asteroid or comet. When most astronomers favored natural explanations, like unusual outgassing or volatile depleted composition reflecting exotic formation conditions, Loeb argued those explanations face their own difficulties, and that artificial origins shouldn't be dismissed without thorough investigation. That episode divided the scientific community in ways still visible in how colleagues discuss these topics. Some appreciated his willingness to think outside conventional bounds, arguing that science advances precisely through challenging assumptions, and considering hypotheses others reject prematurely. They saw value in raising public awareness of SETI and technosignature searches, viewing Loeb's media presence as helpful for securing funding and institutional support. Others cringed at what they perceived as premature speculation,
arguing that proposing alien artifacts without compelling evidence undermines scientific credibility with the public and makes securing support for legitimate research harder when sensational claims don't pan out. Now, Comet Atlas has become the next battleground in this ongoing tension between open-minded exploration and conservative skepticism. Loeb and collaborators have spoken publicly about the possibility of controlled motion, suggesting through technical analyses and media statements that the jet reversal might represent a probe executing maneuvers rather than natural outgassing evolution. The media predictably amplified this angle, always preferring dramatic narratives over nuanced scientific debates. Suddenly, the comet is being called potentially artificial in headlines and social media posts, even though actual scientific consensus among researchers studying the object leans strongly toward natural explanations involving compositional transitions or geometric effects. This is what happens when prominence, media connections, and rhetorical skill draw disproportionate attention to hypotheses that, if proposed by less visible scientists through normal peer review channels, might circulate quietly among specialists without public awareness. That attention has both benefits and costs that are difficult to weigh objectively. More people learn about interstellar objects and the scientific questions they raise. Public interest in astronomy increases, potentially inspiring students to pursue careers in science. Funding agencies notice, potentially directing resources toward follow-up observations and instrument development that enables better characterization of future visitors. But sensational framing can mislead non-experts who lack context to evaluate competing claims. If the public comes to believe this comet is probably artificial, based on preliminary speculation that later proves unfounded, trust in astronomical expertise might decline when the final answer disappoints relative to initial excitement. The damage potentially compounds if one prominent scientist is seen as representative of the field, when in fact, he represents an outlier position in willingness to publicize speculative ideas before they've passed through extensive peer scrutiny. The scientific community struggles with how to handle provocative claims responsibly, balancing openness to unconventional ideas against standards for evidence and rigor developed over centuries. Peer review is designed to filter weak ideas before publication, with experts evaluating methods and conclusions for soundness. But the threshold for publication isn't the same as the threshold for broad community acceptance or textbook consensus. Controversial papers can pass peer review if methods are technically sound, even when conclusions remain disputed. Science thrives on disagreement, on competing interpretations tested against accumulating evidence. But when disagreements spill into public view through press releases and media interviews, non-experts have trouble assessing who's right and how to weight competing claims. Critics suggest that advocacy for exotic explanations is driven partly by personal brand building and self-promotion, leveraging controversial ideas to maintain visibility and influence. Defenders counter that judging ideas based on perceived motive is intellectually dishonest, an ad hominem fallacy. Whether someone benefits personally from a hypothesis is irrelevant to whether that hypothesis is correct. The only valid test is evidence. If observations support artificial origins, previous skepticism was wrong. If they don't, speculation was premature. But proposing testable hypotheses is how science progresses, even when most tests falsify. But motive does matter in subtle ways affecting objectivity. If a scientist is personally and professionally incentivized to make bold claims that generate attention, confirmation bias can intensify unconsciously. Ambiguous data might be interpreted optimistically, seeing signals where skeptics see noise, downplaying alternative explanations that would diminish the claim's significance. Peer review provides some protection, but reviewers face time constraints and can't check everything exhaustively. And review doesn't occur for media statements, which can shape public perception independent of published literature. The media ecosystem amplifies everything it touches, transforming measured scientific papers into headlines screaming about alien spacecraft. Context is lost in translation. Caveats and conditional language that researchers use carefully disappear in summaries written by journalists working under deadline pressure who may not fully understand the science. Nuanced debates among experts reduce to false binaries, artificial versus natural, with complex intermediate possibilities ignored. That reduction does violence to the scientific process, which rarely deals in certainties but rather probabilities, continuously updated as evidence accumulates. Some colleagues worry publicly about precedent and standards. If every unusual astronomical object triggers immediate speculation about artificiality before natural explanations are exhausted, the signal-to-noise ratio crashes. Anomalies are common in vast data sets spanning millions of objects. Most resolve to natural explanations once better data arrive or models improve. Jumping prematurely to exotic claims could desensitize audiences and funding agencies, creating a boy who cried wolf effect, where genuine anomalies get dismissed because too many false alarms preceded them. Others argue that's precisely missing the point. We should be checking unusual objects for technosignatures systematically. The cost of false positives, spending effort on natural objects briefly thought might be artificial, is low compared to the cost of false negatives, missing actual alien technology, because cultural stigma or career risk prevented anyone from looking carefully enough. The next months will test these competing philosophies in real time as more data arrive. If the comet turns out natural, with all anomalies explained by compositional transitions or projection effects, critics will say this proves the folly of premature speculation and the damage it causes to scientific credibility. Defenders will say testable hypotheses were advanced in good faith, observations were proposed and partly executed, and falsification is exactly how science should work. If anomalies persist or strengthen, if observations accumulate that natural models can't accommodate, early speculation will be vindicated as prescient rather than reckless. Either way, the episode will inform how the community handles future controversial objects, shaping standards for public communication and resource allocation for follow-up observations. What's certain, regardless of this particular case's outcome, is that science is fundamentally a social process embedded in human institutions and culture. Data don't interpret themselves automatically. Humans choose which observations to prioritize given limited telescope time and funding. Humans develop models reflecting both evidence and theoretical preconceptions about what's plausible. Humans write papers using language that reveals biases and assumptions. Humans referee those papers, deciding what reaches publication. And humans control resources, determining which projects receive support. Those choices reflect not just logic and evidence, which are paramount in principle, but also career incentives, disciplinary norms about acceptable risk-taking, personal relationships between colleagues, and individual personalities of key actors with influence. Understanding this social dimension doesn't diminish science's power or reliability. Scientific knowledge is robust precisely because social processes like peer review, replication, and public criticism correct individual errors and biases over time. But it does mean that scientific progress is sometimes messy and nonlinear, with detours into ideas that later prove wrong, but were worth exploring. The challenge for observers, both specialists and interested public, is maintaining appropriate skepticism toward dramatic claims, while remaining open to genuinely revolutionary discoveries when evidence warrants changing minds. Let's imagine for a moment the scenario that seems statistically improbable but logically possible. Picture the situation where months from now, after perihelion passage and intensive follow-up observations, after all natural explanations have been tested systematically and found wanting, the scientific community gradually reaches consensus that defies prior expectations. The comet is not natural. It exhibits signatures that cannot be reconciled with known physics of ice and dust and gravity. It's something made, designed, scent. What would it take to believe that? The bar must be, and should be, extraordinarily high, precisely because the claim is so extraordinary, so far outside accumulated experience and theory. You'd need multiple independent lines of evidence, each one strung by itself, together, overwhelming. Start with sustained non-gravitational acceleration quantitatively inconsistent with sublimation models, even after exploring full parameter space. Not just small orbital residuals comparable to measurement uncertainties that could be instrumental noise or modeling errors, but clear, systematic deviations, showing the object is accelerating in ways natural outgassing wouldn't produce, given observed mass loss rates. The acceleration would need to persist too long temporally, continuing well after thermal models say volatiles should have stopped sublimating as the comet moves far from the Sun and cools below sublimation thresholds. Or, if thrust turned on and off in discrete episodes rather than varying continuously following solar heating, that pattern of discrete burns would demand explanation that outgassing struggles to provide. Repeatable changes in jet orientation matter crucially in this context. If the object reoriented its emission axis multiple times over the observational campaign, each time in ways uncorrelated with solar heating variations or rotational state that should drive natural cometary jets, you'd have to ask seriously what's controlling the direction. Natural comets have jets tied physically to active regions on the nucleus, specific locations where volatiles are concentrated and where overlying dust layers are thin enough that sublimation can break through. Those regions stay fixed relative to the rotating body. As the nucleus spins, jets sweep around, creating predictable patterns in brightness and morphology that observers can model using shape models and thermal calculations. Arbitrary reorientations unconnected to rotational state would suggest something external is controlling emission direction, implying actuators or control systems capable of steering thrust vectors. Spectral anomalies would carry tremendous weight as evidence. If spectroscopy, splitting light into wavelengths and measuring intensity at each, revealed emission or absorption lines from metals, like aluminum or titanium or iron, in forms inconsistent with refractory dust heated by sunlight, that would be a red flag demanding investigation. Comets are made fundamentally of ices and dust, primitive material from solar system or interstellar cloud formation that never got hot enough to melt and differentiate. They shouldn't contain manufactured compounds, alloys, or processed materials. Detection of such signatures would require exotic explanations, with artificiality prominently on the list, simply because natural processes struggled to produce them. Radio or infrared emissions could help decisively. An artificial object might emit electromagnetic radiation, either intentionally as communication beacons, signaling to whoever might be listening, or unintentionally from internal systems like power generation, data processing, environmental maintenance, or simply waste heat from active electronics and machinery. Radio telescopes have listened to various anomalous astronomical objects over the decades, pointing their sensitive receivers toward pulsars that turned out to be natural neutron stars, fast radio bursts that proved to be magnetars in distant galaxies, and other phenomena that initially seemed artificial but weren't. But they've rarely pointed at solar system objects moving through near-Earth space, on the off chance they might be transmitting. If this comet emitted narrowband radio signals modulated in non-natural patterns, showing information content or temporal structure inconsistent with thermal emission, that would be extraordinary evidence. Even thermal radio emission with unexpected spectral properties could hint at internal heat sources beyond solar warming. Then there's trajectory analysis, examining whether the orbit itself is special in ways that suggest design. Does it approach the inner solar system at an angle or speed that seems too convenient, too carefully chosen to maximize observation opportunities? Interstellar objects arrive from random directions with random velocities, determined by their ejection from home systems billions of years ago, and their subsequent path through the galaxy governed by encounters with molecular clouds and stellar gravity. If this comet's trajectory showed fine-tuning that raises eyebrows among orbital dynamicists, parameters that seem selected rather than random, suspicion would grow. However, defining what constitutes suspicious fine-tuning remains subjective and contentious. With a sample size of only a few known interstellar visitors, documented over a few years, we don't yet know what the typical statistical distribution of orbits should look like. Claiming an orbit is anomalous requires establishing the baseline of normal, which we simply don't have yet. The combination of evidence matters more profoundly than any single observation standing alone. One anomaly can be explained away with sufficient creativity and parameter tuning. Natural phenomena are complex and varied. Observational data always contain noise and systematic errors. Given enough degrees of freedom in models, almost any single observation can be accommodated. But if you stack up sustained acceleration plus spectral anomalies plus radio emission plus trajectory fine-tuning plus morphological changes uncorrelated with expected physical drivers, natural explanations become increasingly strained. At some point, determined by community judgment rather than mathematical formula, invoking multiple unlikely coincidences becomes less parsimonious than accepting the hypothesis that something genuinely unusual, potentially artificial, is occurring. Verification protocols would need to be extraordinarily rigorous to handle a claim this consequential. Independent observatories must replicate every finding using different instruments and different methodologies to eliminate instrumental artifacts and confirmation bias. Multiple analysis teams should examine raw data separately, processing it independently with different pipelines and checking whether they reach consistent conclusions. Statistical significance must be overwhelming, with p-values approaching what particle physicists demand for new fundamental particle discoveries. Thresholds of 5 sigma or higher representing less than 1 in a million probability of random fluctuation. Peer review must be maximally open and adversarial, with confirmed skeptics given full access to data and analysis code so they can search exhaustively for errors or overlooked alternatives. The geopolitical dimension would activate immediately if artificiality were confirmed or even became seriously plausible. Who owns the discovery, intellectually and legally? Which nation or institution gets historical credit? Does artificial mean active technology from a currently existing civilization somewhere in the galaxy? Or does it mean an ancient artifact launched millions of years ago by a species long extinct? If it's a probe from an active civilization still operating, are they watching us now through instruments we can't detect? Are they aware that we've noticed their probe, and might they respond somehow? Should humanity attempt communication, pointing radio telescopes at the object and transmitting signals hoping for a response? These questions leap immediately beyond pure science into diplomacy, security policy, and philosophy. No actual tested protocol exists for handling an artificial object entering the solar system. Plans exist on paper for what to do if SETI detects a radio signal from distant stars, involving verification and international coordination before any response is sent. But a physical object in our immediate neighborhood presents different challenges and opportunities. Would governments attempt to classify information, keeping discoveries secret for security reasons, or would scientific transparency prevail? The answer might depend critically on what the object does, whether it seems passive, like a reconnaissance probe recording data, or active and potentially reactive to our presence. Mission concepts to physically intercept this comet would face brutal engineering and scheduling constraints that might render them infeasible given current technology and timelines. The object is moving at high velocity on a hyperbolic escape trajectory. After passing perihelion, its closest approach to the Sun, it will be racing back out of the solar system at speeds exceeding 40 kilometers per second relative to the Sun. Catching it requires a spacecraft capable of enormous velocity changes, measured in tens of kilometers per second, delta V in engineering terminology. Chemical rockets, the workhorses of current space exploration, can't achieve that with reasonable spacecraft mass ratios. The rocket equation is tyrannical, demanding exponentially increasing fuel mass for linearly increasing velocity change.
Nuclear propulsion might work in principle, using fission reactors to heat propellant to temperatures chemical reactions can't reach, achieving higher exhaust velocities and therefore better efficiency. But nuclear rocket engines exist only as ground-tested prototypes, never flown in space, requiring years of development and flight testing before they could be trusted for an interstellar intercept mission. Solar sails or laser-pushed light sails could build speed gradually over time by using radiation pressure, but probably not fast enough to catch an object already racing away. Interception scenarios studied by mission designers suggest launch windows closing months after discovery, requiring development timelines impossibly compressed compared to normal space mission cadences, measured in years to decades from concept to launch. Fast flyby concepts represent the only plausible near-term option if resources and political will materialized. Small probes, perhaps CubeSat-scale spacecraft mass-produced cheaply, launched on minimum-time trajectories by the largest available rockets to intercept the object while still within a few astronomical units of the Sun. These wouldn't rendezvous, achieving matching velocities to fly alongside the comet, which would require even more delta-v. They would just zip past at high relative velocity, measured in tens of kilometers per second, snapping images and spectra during a brief encounter lasting seconds to minutes. Even that limited mission profile would require rapid development timelines and significant funding, appearing on timescales of months, essentially impossible through normal budgetary and approval processes. The probability of securing approval through NASA's standard procedures or equivalent international space agencies approaches zero, simply because committees and review boards and appropriations subcommittees don't move that fast. Alternative approaches involve long baseline observation campaigns rather than physical intercept. Continue tracking for years as the object recedes, monitoring for any behavior changes, radio emissions, trajectory adjustments, or other signatures that might become detectable even at increasing distance. Deploy new dedicated assets, perhaps small space telescopes optimized specifically for faint object tracking, launched into solar orbit, where viewing conditions remain excellent year-round, without Earth's atmosphere or daylight constraints. The data accumulated might never be definitive in the sense of achieving absolute certainty, but gradual accumulation of evidence over time could shift community probabilities toward or away from artificial hypotheses, building cases through weight of consistent observations. If artificiality were somehow confirmed through this process, passing every test and withstanding every attempt at falsification, the implications would cascade outward through every domain of human thought and activity. First and most obviously, we're not alone in the universe. That conclusion has been suspected based on statistical arguments about the size and age of the cosmos, even assumed by many scientists and members of the public who consider it almost certain that life and intelligence have arisen elsewhere. But knowing is fundamentally different from suspecting. Proof of extraterrestrial technology, physical evidence that we can point to and say definitively this came from beyond Earth, would be the most consequential discovery in human history, measured by its impact on worldviews, reshaping philosophy, religion, science, and our collective sense of cosmic significance. Second, interstellar travel is demonstrably possible, not just theoretically allowed by physics, but actually achieved by at least one civilization. If someone sent a probe across light years of deep space successfully, the engineering challenges we consider nearly insurmountable have been solved by someone. That suggests civilizations can persist long enough to develop such capabilities, despite all the risks of war, environmental collapse, resource depletion, or other catastrophes that might terminate technological species before they achieve star travel. It also suggests the galaxy might be thick with such probes, a network or archaeology of exploration, left by multiple species over billions of years, most passing through solar systems undetected, because inhabitants lack technology to spot them.
Third, we'd have to reconsider previous anomalies in our astronomical catalogs retroactively. Was Oumuamua Artificial 2, that first interstellar visitor showing unusual acceleration without detected outgassing? Should we re-examine archival data looking for other objects that pass through unrecognized? How many interstellar visitors have transited the solar system in the decades since we've been taking systematic surveys, missed because they were too faint or not recognized as unusual? The discovery would trigger intensive retrospective analysis, searching through decades of telescope images and astrometric databases for patterns we missed. Objects dismissed as asteroids that might deserve second looks. Fourth, profound implications for humanity's future trajectory. If others have achieved interstellar capability, we might too, eventually. If civilization survives its current challenges and continues developing technology, the feasibility of star travel becomes less speculative abstraction, more concrete engineering challenge that advanced civilizations demonstrably solve. Funding and political priority for projects like breakthrough propulsion research, interstellar probe studies, and SETI expansion could shift dramatically once we know for certain that someone else succeeded. Maybe we're seeing trail markers of older civilizations, breadcrumbs marking that others passed this way, and our destiny, if we survive, is to eventually join that community of starfaring species. Or maybe we're seeing remnants of extinct societies, civilizations that rose and fell and left only their silent probes drifting through the galaxy as monuments, serving as warnings about challenges ahead that we'll need to navigate to avoid similar fates. The null hypothesis remains vastly more probable based on prior expectation and current evidence. This comet is almost certainly natural, an unusual but ultimately explicable visitor from another planetary system with properties reflecting exotic formation conditions and compositional evolution we're still learning to understand. The compositional transition model from carbon dioxide to water ice probably explains most or all observations, once viewing geometry and grain dynamics are properly modeled. The engineered object hypothesis will likely fade from serious consideration as more data arrive and natural models improve, joining the long historical list of initially intriguing astronomical anomalies that resolved to mundane explanations once observers looked more carefully. But the exercise of considering seriously what artificial would mean, working through what evidence would be required and what observations to prioritize, is worthwhile even if probability is tiny. It clarifies thinking, distinguishes testable predictions from vague speculation, identifies what follow-up makes sense given resources, and it highlights the profound asymmetry in outcomes. If natural, which is likely, we learn interesting things about interstellar comet science, characterize compositional diversity among objects from other stellar systems, maybe discover new sublimation regimes or grain dynamics. Then we move on to other questions. If artificial, even if probability is 1 in 1,000 or 1 in a million, everything about humanity's cosmic context changes, permanently. That asymmetry, the enormous difference in significance between the two outcomes, justifies careful scrutiny, with appropriate resources, even when probability seems low. A revolution in how we watch the skies is beginning right now, as new survey telescopes come online, and the implications for finding and characterizing objects like this comet are genuinely transformative. The Vera Rubin Observatory achieved first light late in the year, marking the beginning of an ambitious program that will revolutionize our ability to detect and track transient and moving objects across the entire visible sky. Rubin's design is purpose-built for wide-field surveying rather than deep-pointed observations of single targets. Its telescope has a large primary mirror measuring 8.4 meters across, providing excellent light-gathering power, paired with an enormous camera containing 3.2 billion pixels, one of the largest digital cameras ever constructed. Together, they can image areas of sky measuring about 40 full moons across in a single exposure. Unprecedented field of view for a facility-class telescope. More importantly for transient and moving object science, Rubin will repeatedly scan the entire visible sky every few nights throughout each year, weather permitting, creating a time-lapse movie of the universe, showing how everything changes on timescales from minutes to years. That observational cadence changes the game fundamentally. Traditional astronomy often revisits the same patches of sky months or years apart at best, sufficient for studying static objects like distant galaxies, but inadequate for catching fast transients. Rubin's approach, imaging each part of sky multiple times per week, means anything that moved or changed pops out immediately when you compare images taken days apart using sophisticated difference imaging pipelines that subtract earlier images from recent ones. Asteroids reveal themselves by shifting position relative to background stars, appearing as trails in images or as point sources at different locations in successive frames. Supernovae appear as new bright points in distant galaxies where nothing was visible days earlier. Comets, including critically those on interstellar trajectories, show up as fuzzy moving objects, distinct from both sharp stars and static extended galaxies. The difference imaging and automated detection algorithms that process Rubin data will flag these moving transients for follow-up, potentially within hours of observation, enabling rapid response before objects fade or move out of range. The statistical implications are profound for interstellar object science specifically. Right now, we've confirmed only a handful of interstellar visitors over several years of searching, far too small a sample to draw meaningful conclusions about the population. Are interstellar comets common, with dozens passing through the inner solar system annually, or rare, with one every few years? What fractions show cometary activity versus appearing inert like asteroids? Do they have unusual compositions, systematically different from solar system objects, reflecting different formation environments around other stars with different compositions and irradiation histories? Rubin will answer these questions definitively by discovering interstellar visitors at dramatically higher rates. Projections based on survey depth, cadence, and assumed interstellar object population density suggest detection rates of dozens per year once the survey reaches full operation and optimal analysis pipelines mature. That abundance transforms interstellar object science from anecdotal case studies of individual unusual objects to statistical population studies that can constrain formation mechanisms, galactic dynamics, and the diversity of planetary system architectures across the galaxy. Early warning becomes another transformative capability. This comet was discovered relatively late in its approach, already inside Earth's orbit and approaching perihelion rapidly, leaving limited time for planning intensive follow-up campaigns and coordinating multiple observatories. Future interstellar visitors detected by Rubin will be caught earlier, perhaps years before closest approach, while still in the outer solar system, beyond Jupiter's orbit. Discovering them early allows years-long monitoring campaigns, tracking activity evolution over huge ranges of heliocentric distance, constraining sublimation thresholds for different volatile species, watching nucleus properties evolve as thermal waves penetrate inward. The survey will also create an invaluable archive that grows with time. Every patch of sky gets imaged multiple times across multiple filters measuring different wavelength ranges over years. That archive can be searched retroactively whenever new objects are discovered. When a new interstellar comet is found, astronomers can look back through archives searching for prediscovery detections, moments when the object appeared in earlier images before anyone recognized it as interesting. Those prediscovery detections extend the observational baseline backward in time, improving orbit determination and providing activity history that would otherwise be lost. Imagine if Rubin had been operating for the past several years. This comet might have been detected much farther out in the solar system when it was still faint and inactive, visible, but not yet bright enough to trigger alerts. Early spectroscopy could have characterized composition before major outgassing began. The entire evolution from dormant ice ball to active comet to jet reversal would have been documented continuously, rather than pieced together from sparse snapshots, separated by weeks. This raises an intriguing question worth pondering. How many objects similar to this comet have passed through the inner solar system completely undetected over the decades before systematic surveys existed? We've only been searching comprehensively for unusual objects on hyperbolic orbits for a few years. Before that, any visitor on an interstellar trajectory might have been noticed if it passed close to Earth and brightened substantially, but most would have gone undetected if they remained faint or stayed far from our planet. Rubin changes the detection threshold dramatically, an order of magnitude improvement. Its sensitivity and comprehensive cadence mean that fainter, smaller, more distant objects become discoverable routinely, rather than requiring lucky circumstances. The data volume generated by Rubin is staggering and presents its own challenges. The survey will produce tens of terabytes per night, raw images that must be processed through sophisticated automated pipelines to subtract previous observations, detect transients and moving objects, measure their properties, and classify them. Machine learning algorithms increasingly handle classification, trained on large datasets to distinguish asteroids from comets, from supernovae, from variable stars, from instrumental artifacts. The stream of alerts flowing from these pipelines, potentially millions of detections per night, including both real objects and false positives from cosmic rays or satellite trails or processing errors, feeds into follow-up networks where human observers and smart scheduling systems decide what deserves deeper investigation with specialized instruments. This automated infrastructure represents the future of observational astronomy, necessary to handle data volumes that far exceed human capacity for manual review. No single person or even large team can look at millions of alerts each night. Algorithms prioritize based on criteria like novelty, rarity, brightness, how well detections match predicted signatures of interesting phenomena. Candidates that pass algorithmic filters get flagged for human review. Really interesting ones showing truly unusual characteristics trigger rapid follow-up requests to specialized instruments capable of obtaining spectra, high-resolution imaging, or other detailed measurements that characterize objects beyond what survey data provides. For interstellar objects specifically, the detection signature is distinct but subtle, requiring careful analysis. Unusual orbits with high eccentricity, approaching or exceeding the escape threshold, separate potential interstellar visitors from bound solar system objects. But measuring orbital eccentricity requires multiple detections spanning days to weeks, as the object moves measurably against background stars. A single detection can't distinguish interstellar from a poorly determined elliptical orbit. Automated tracking pipelines must link detections across multiple nights, fitting preliminary orbits and flagging those with parameters suggesting extrasolar origin for priority follow-up that refines trajectories and confirms or rules out interstellar status. The human element remains crucial despite automation. Automated systems excel at identifying candidates, but human judgment and expertise decide what's genuinely interesting enough to mobilize expensive follow-up resources. Spectroscopy requiring hours on large telescopes, high-resolution imaging campaigns, intensive monitoring programs, all require human decisions about resource allocation, balancing competing demands from many scientific programs. Rubin amplifies the discovery rate enormously, but the community must scale up follow-up capacity proportionally to avoid becoming overwhelmed with candidates that can't all be characterized adequately. International collaboration becomes more important than ever in this new era. No single institution or even single nation can follow up on all interesting targets discovered by next-generation surveys. Distributed networks of telescopes coordinating observations help, with facilities in different hemispheres providing continuous coverage as Earth rotates. Observers share data rapidly through astronomical telegrams and central archives, coordinate to avoid duplication of effort, and collectively build comprehensive data sets on transient events. The culture of astronomy has long embraced open data sharing and international cooperation, increasingly formalized through structured programs and data repositories. Looking forward, the Rubin era starting now will likely include many discoveries similar to this comet. Interstellar visitors exhibiting unusual, but ultimately natural behavior. Some will be straightforward, icy comets resembling solar system counterparts, except for their hyperbolic orbits. Others might be genuinely exotic, with compositions or structures reflecting formation conditions wildly different from our own system's history. A few might be genuinely anomalous, showing characteristics that challenge our understanding in ways that take years to explain. The key is having robust systems in place to distinguish routine from genuinely unusual, allocating attention and resources wisely, and avoiding both missing real anomalies through inadequate follow-up and overhyping routine discoveries through premature speculation. The revolution is not just technical, but cultural, representing a fundamental shift in how astronomy operates. The field is transitioning from small-team, single-target studies, one astronomer studying one object in depth over years, to large-scale collaborative surveys and big data analysis, where hundreds of researchers work on projects processing millions of objects. That transition requires new skills in data science, machine learning, and statistical analysis, beyond traditional observational techniques. It requires new infrastructure, including massive data centers, cloud computing resources, and sophisticated software pipelines maintained by large teams. And it requires new organizational models for collaboration, coordinating efforts across institutions and national boundaries more seamlessly than the individualistic culture of past astronomy encouraged. For anyone interested in interstellar visitors and the questions they raise about planetary system diversity and potential technosignatures, the next decade promises to be extraordinary. The trickle of discoveries that has characterized recent years will become a flood. Sample sizes will grow from handfuls to hundreds, enabling statistical analysis that finally answers population-level questions. We'll learn whether recent visitors like this comet and Oumuamua are typical or unusual outliers. We'll constrain formation mechanisms, testing whether interstellar objects form like solar system bodies or through different processes. We'll map the distribution of trajectories and velocities, learning about galactic dynamics and how objects get ejected from home systems. And, just maybe, we'll find something that doesn't fit any natural model. Something that demands we seriously consider possibilities we've barely begun to contemplate. The universe is vast. The galaxy contains hundreds of billions of stars, many with planets. Other civilizations, if they exist, might explore using probes we could detect if we look carefully enough. Most objects will be natural, but the cost of checking is small compared to the potential significance of finding even one artificial visitor. That's the bet Rubin and other next-generation facilities represent. Systematically searching vast swaths of sky, catching everything that moves or changes, and building the data sets that let us distinguish extraordinary from ordinary with confidence. This comet, whatever it ultimately turns out to be, represents a preview of what's coming. A decade from now, we'll have characterized dozens of similar visitors. We'll know their typical properties, we'll have refined models explaining their behavior, and we'll be better positioned to recognize when something truly doesn't fit. When all natural explanations fail, and we're forced to consider alternatives that would transform our understanding of our place in the cosmos. That's the promise of the era beginning right now, an age of discovery just opening, where the universe reveals more of its secrets faster than ever before in human history. The next chapters of the story will be written in the data arriving from telescopes around the world and in space. The observations made over the coming months as this comet fades into the distance will either resolve current questions or deepen mysteries. Either outcome teaches us something. Either outcome advances our understanding. And that's, ultimately, what drives science forward. The willingness to look carefully, to test ideas rigorously, to follow evidence wherever it leads, even when destinations surprise us. Whatever truth awaits regarding this particular visitor, the search itself embodies the best of human curiosity and our endless quest to understand the universe we inhabit.